Hi, so today I'm going to explain what a buck converter is, how that works, what it does. A buck converter is pretty much a system that takes a higher voltage and slices it up until it becomes a lower voltage. So you take this higher power line, and it's still a high power, it's still a high voltage. So let's say you have 16 volts. You take your 16 volts, that would usually be flat, and you slice it up. So you have 16 volts, nothing. 16 volts, nothing. 16 volts and nothing, and you average that out to get yourself to a lower power. So we use this to turn 12 volts into 1 volt for CPU vCore. We use this to turn 16 volts from the charger into 12.6 volts for the system to run off of. And let me just show you a couple of examples of how this works here. So now remember what I talked about with transistors? Remember how I said a transistor is pretty much a resistor whose resistance is variable? So these are two transistors over here. So you have this one over here and this one over here. And their resistance is going to vary based on the signal at the gate. So the way this works is you have the charger power coming in over here from the machine. So this over here is the 16 volts that your charger is sending through. So it's approximately 16 or 18 volts. I don't remember off the top of my head. I should, because I work on these machines like 15 times a day, and I don't remember off the top of my head. Anyway, that is about 16 or 18 volts from the charger coming here. And remember, we need to turn that into 12. So what this transistor over here is going to do is it's going to turn on and off very, very quickly. And it's going to do that in sync with this transistor down here. So this transistor is going to ground, which is going to create a path for this power to come through. And this over here is going to open, and so that it sends power this way to the computer. Now, these two transistors are going to open based on signals coming from the gate from this chip. So a buck converter is not just two transistors. A buck converter is also controlled by another chip that is going to be telling it when to switch on and off. So remember, if you're switching it on and remember how you're switching it on and off is going to determine how much power you use. So let's say you have, okay, let's say this is your 18 volts, right? So I'm going to draw 18 volts up here with a line. So let's say this is 18 volts. So that's this is 18 volts, 18V. Now, what do you think is going to give you more power? 18 volts like this, okay. Now, what do you think is going to give you more power? 18 volts like this with just a couple of cutouts, like so, like just a few? Or do you think you're going to get more power when you have 18 volts, but you have this really slow switching? Or do you think you're going to have more power when you have something that looks like this? Obviously, this is going to give you more power than this because you have more slices of 18 volts. So if you want to turn a higher power into a lower power, the thing is you need to know how quickly you need to be switching, how long do these transistors need to be open, how long do they need to be closed for, how fast should they be switching on and off so that you can get your desired output power. And that's going to be dependent on the input power and the output power that you want. So that's pretty much how this works. So this chip over here has to know when to switch these on and off to get your desired output voltage. Now, over here, another component of any type of buck converter, you have an inductor over here, which is only going to allow the DC to pass through, and it's also going to have a capacitor in front of it that's going to smooth all those pulses. Because again, this over here, this is not 12 volts. This is just a bunch of slices of 18 volts. So you have a slice and then nothing, and then a slice and then nothing. So on a proper graph, so let's say that's 18 volts over here. Let's just show you what this should look like if this graph were actually done the right way. So let's delete all this over here. So let's say we make a line. So let's say this is 18 volts. And let's say that's 0 volts, right? So the way that what I did is going to be doing, it's going to be doing something like this. So it's on. So every time that thing switches off, you're down to 0 volts. Like this. And the system is going to average that out. So it's going to average out the amount of time. So it's going to average out the amount of voltage and the amount of time there to come up with the output voltage. So it's going to think that you have 12 volts because you have 18 volts and then 0, 18 volts and then 0, 18 volts and then 0, 18 volts and then 0. Obviously, the longer you stay at 18 volts and the more pulses of 18 volts you have, the closer to 18 you'll be at, and the longer you stay at 0 and the more pulses of 0 you have, the closer your voltage will be to 0. So this is going to be really confusing until I simply show you it on the oscilloscope. So what I should do at this point is just shut up and show you it with a picture so that it makes actual sense in a real world circuit. So what I'm going to do is I'm going to find these two transistors, Q7030, Q7035, and I'm also going to find the inductor over there so I can show you how this works. So again, one last time, these transistors are going to switch and take these pulses of the 18 volts from the charger, and you're going to see a bunch of pulses over here. This chip is going to control these two transistors, telling it when to turn on and turn off, turn on and turn off, so we have the proper duration of those pulses to create 12 volts. The inductor is only going to pass DC well, so between the inductor over here and this smoothing set of capacitors over here, this is going to turn that higher 18 volts of pulses, and it's going to make it into one flat 12.6 volts. Okay, so let's start here with the components of a buck converter. So over here we have the top of the first transistor, Q7030, right? Let me show you what that looks like. Now that's going to be the charger voltage. Obviously, you can't see that because I have the voltage here set too low. So that is 17 volts. That's what we have. That's the charger power. Now, here is what you get on the gate of that transistor. So on the gate of that transistor is right over here. It's a bunch of pulses. Let's see what it looks like a little up close. So see, that's every single time that thing is opening, you're getting a switching. See, it's telling it on, off, on, off. It's sending the signal to tell the source of this transistor. So the source is this. So every time you get a pulse over here, this is opening and you have power going through. And here's where you can actually see the power going through. This is the pin with the power going through. Now over here it says the average voltage is 13, 14, somewhere around there. See, that's pulses of charging power. So that's not a straight line. It's 17 volts and then 0. That's 17 for this long and then 0 for this long. Now let's see what it looks like on the input of the inductor. So on pin 1 of the inductor. Pretty much the same thing. Now let's see what it looks like outside the inductor. So on the other side of the inductor, after it's been through the inductor, and on the side with the smoothing capacitors over here. So just to show you, let me get the smoothing capacitors in view. So you have the inductor, and then the smoothing capacitors over here. On the other side, you get something that looks like this. It's flat. It's a nice, flat, even 12 volts. See? No pulsing. You have minimal rippling. You can see a little bit of rippling, but that's negligible for a laptop charging circuit. And you have these buck converters for many other parts of the machine. So let's take a look and see look at the CPU vCore. So here, let's take a look at this one. Now let's look at CPU vCore. See, it's the same general principle. It's the same thing over and over and over again. So you have two transistors. you have two transistors, you have an inductor, you have a smoothing capacitor after the inductor, and it's pretty, and you have this controller over here that's actually telling these two transistors when to open, when to close, and it's sending pulses to the gate. So again, same general idea. So here's with CPU vCore. Now over here, here's what you're going to notice compared to before. It's the same general idea, except we're turning, instead of turning 17 volts into 12, we're trying to turn 12 volts into 1. So you're going to have much thinner spikes of 12 volts and much larger spikes of 0. So over here, what you're going to see, for this part of the circuit, you see that the spikes of 0 are very small, but the spikes of 12, so over here you're going to see that the spikes of the input voltage are very long, and the spikes of 0 volts where it's turned off are very short. That's because we're trying to turn a high voltage into a slightly less high voltage. But when you're trying to turn a high voltage into a low voltage, you're going to see, again, this is just basic math here. It's basic averaging. You know, again, like think of it like this: like 12 plus 0 divided by 2 is 6. 12 plus 0 plus 0 divided by 3 is 4. 12 plus 0 plus 0 plus 0 divided by 4 is 3. 12 plus 0 plus 0 plus 0 plus 0 plus 0 plus 0 divided by 6 is 2, and so on and so forth. So if you want a lower voltage, you simply have longer periods of the transistor being off and not sending voltage, and shorter periods of it being on and sending voltage. And on the other side, again, what you're going to get with this type of system is pretty clean. You're going to have a nice lower voltage that doesn't look like a bunch of pulsing messes. You're just going to have a nice flat one, well, not totally flat, but flatter than the before nonsense. Yeah, 1.17 volts. Yeah, if you zoom out a little bit on the axis, then it looks cleaner. And that's that. That's pretty much what a buck converter does. So every time you see that in a circuit, every time you see this thing, this general thing, where you see a controller chip, you see two transistors, one between a high voltage power line and one at output, one between output and ground, and you see an inductor over here and a capacitor after it. The purpose of that circuit is to turn a higher voltage into a lower voltage. That's the whole point. And again, unlike a voltage divider, which I've mistakenly called this in other videos when it was 3 in the morning and I was dead tired, this is much more efficient. This is, like, again, if you had a voltage divider running all these different sections of the computer, your battery would last for maybe 10 minutes and your computer would probably go on fire in your lap. It would be that hot. So this is a much more efficient way of switching a high voltage to a lower voltage without really wasting much energy. And that's about that.